So today we're talking about clustering and cluster analysis. So clustering is a form of unsupervised learning. So we've been learning about a type of supervised learning since the start of the semester, and that's when our data is labeled. It comes with labels already there, like the class or the numerical output. So with those, we use supervised learning. Now, if our data is unlabeled and we do not have access to labels, then we can use another form of learning that's called unsupervised learning. And one form or one type of unsupervised learning is clustering and cluster analysis. So with cluster analysis, we're trying to find similarities between the data according to some sort of characteristics that we can find in the data, and then we put them into clusters or groups. So every group will gather data points or data instances that are similar. Okay, and so the triangles are different than the circles, and so we're going to put all the circles together in one cluster and all the triangles together in another cluster. So clustering analysis is based on similarity. So clustering can be either used as a separate standalone uh, tool to gather information about the data distribution, um, or we can use it as just a preliminary stage or a pre-processing stage where we are just trying to look and inspect the distribution of our data before we get into the next stage in the analysis. So clustering has many applications today and these are some of the examples of field applications of cluster analysis. We can think of marketing, for instance, where we want to put the customers into similar customers into groups or clusters, and then we do targeted marketing where we are targeting specific types of customers with accustomed or specific types of ads. And so if we're using clustering as a pre-processing tool, then once we plot our data and we look at the different groupings inside our data, we can easily spot outliers, for instance, those data instances that are far away from any group in our data will be considered an outlier. We can use also unsupervised learning as part of the attribute selection that we talked about before, and one type of attribute selection algorithm called PCA, and it is a type of unsupervised learning. And so if we want to know how good our clustering algorithm is, there's different measures and metrics to consider. So things like the intra-class similarity. So we want the instances that belong to the same cluster to be as similar as possible, whereas other instances that belong to the other cluster, we want them to be as different as possible. And so there are different characteristics or considerations that we have to think about when we want to build our clusters. Things like what's the similarity measure that we can use? What are we going to base our clustering algorithm on? How can we define similarity? Okay, how can we implement it? And then how good are those clusters at identifying those interesting patterns that we're looking for in our data? So one way to represent a similarity is using a distance function. We can somehow come up with a distance function to represent how similar data is using this metric. And also there are different types of clusters and clustering algorithms. Some of them are based on a single level, some of them are really hierarchical, and you can have multi-levels of clusters. And then also when it comes to the separation of clusters, some clustering algorithms will have exclusive membership of instances to one cluster. So an instance can only belong to exactly one cluster, versus non-exclusive algorithms can give sort of probability to an instance to belong to all of the existing clusters. So we can say that this instance have a 0.8 probability of belonging to class 1 and 0.2 probability of belonging to class 2. So we call these non-exclusive type of clustering algorithms. So there are different algorithms and models to do cluster analysis. Some of them are partitioning based, some of them are hierarchical based, density based, grid based. So we're not going to have time to cover all of these, but I want to introduce you to a partitioning based algorithm that is called k-means. So the way k-means clustering works is the following. So the first step is choosing k. So k represents the number of clusters in your data. So you're gonna say, I don't know the classes, so how would I know how many clusters are in my data? So with k-means, you are choosing a random k, or you can choose your prior knowledge of your data to kind of try and estimate what k could be, okay? But the main drawback of k-means clustering is you do need to specify what k is. So you randomly choose k. So once you choose the number of clusters, then you assign each instance to its closest cluster center based on the Euclidean distance. So you're going to calculate the Euclidean distance from that instance to all of the k centers that you've randomly chosen initially. And then once you do that, you recalculate the cluster centers by recomputing the averages, right? The means, that's where k-means comes from. And then once you calculate the average of the instances that belong to each cluster, you keep repeating this procedure until those cluster centers don't move anymore. Then that's the stopping criterion of this algorithm. And so if we're going to try to apply k-means clustering to this example, so we're going to say, okay, we're going to randomly choose k equal 3, okay? This means that I'm saying that my data will have 3 classes. And so I'm going to randomly choose 3 centers, okay? So in this case, I've chosen this center, and this center. So initially they're random, as we said, okay? And so what we're gonna do is we're gonna calculate the Euclidean distance of each instance to the centers and then assign it to the closest one. For example, if we're talking about this instance, I'm gonna calculate the distance to the square center, the distance to the circle center, and the distance to the triangle center. And I'm gonna found that this is the closest one. Therefore, my instance will belong to the square center, okay, or the square cluster. And I do that for each one of these instances. So once I do that, then I'm gonna end up with 3 different groups. And then what I will do is recalculate the center of these instances, as well as these instances, okay? So you can see that the centers have moved from their original positions, right? Based on the first iteration. So once I did that, then again, I'm gonna calculate the distance from each instance to each one of these three centers and then assign it to the closest one. And then once I do that, I will recalculate the centers of my clusters. And then once I notice that in the next iteration, the centers didn't move at all, they remained in the same position, right? As you can see here, from this iteration to this iteration, the centers didn't change after recalculating them, then we know that this is the end of the algorithm. There's no more iterations possible. So this is an animation that shows the movement of the initially randomly chosen cluster centers from an iteration to another. So this one shows 10 different iterations, and you can see the instances change in color from an iteration to another, meaning that after we've recalculated the Euclidean distance, we figured that the other class is the nearest one, and so we change the assignment of clusters. So k-means clustering is an efficient algorithm. However, it suffers from some drawbacks. The first disadvantage is the fact that we have to randomly choose k, right? And it really varies and very sensitive to that choice of the initial random cluster centers, right? And then the other problem is the fact that we are changing the position of those cluster centers based on the similarities, on the Euclidean distance of the instances to it. And so that makes it really sensitive to outliers and noisy data, because those cluster centers will change based on those outliers, okay, which will give you inaccurate clustering results. So you may say that the fact that we have to calculate the distance from each instance to the cluster centers may make k-means algorithm really slow. Well, there are some data structures that can really speed up that process. Examples, KD trees and ball trees. So I'm not going to go into details about how to implement these data structures, but just understand that they're there to speed up the process of having to calculate the distance from each instance in your data set to each cluster center. And so again, Weka has the option to do clustering. So if you want to run clustering, then you can choose the cluster tab, and then you can choose k-means clustering as a cluster analysis algorithm, and then as one of the parameters you can choose the initial number of clusters. And once you run the clustering algorithm, then you do have the option to right click on the result right here and then choose visualize results, and then you can choose the X and the Y. So these are the attributes that you want to visualize your data to, so you can see it in 2D. So you choose two attributes to plot in the X and Y, and you can see here the 3 different clusters in your data visually. So I provided this example, I provided a notebook that has an example of how to run clustering in Python. So it's a simple example for the IRIS dataset that will end up showing you how to choose the number of clusters using one method that's called the elbow method, and it's also showing you how to call k-means, run it, and then visualize the results in 2D. You can take a look at the example if you wish.